Here we are for the very first session of this 5-day GAN course. The first session will be taken by foreign faculty of this course, Professor Jose Maria. Already we heard him during our inaugural session. So I think it is good time to have the session from him without wasting more time. So I request Professor Jose Maria to take the charge of this session. Thank you, sir.
Thank you. Good morning again, everybody. First, I would like to apologize because my English is very Latin. So hope you can understand me, or even the opposite. If you ask me any questions, maybe I will not understand you because your accent. So we will find a way to understand each other. Yeah. Please feel free to raise hands and make questions during the presentation. Otherwise, it will be very boring if I am just talking. So, any question, please feel free. This is the title of the course that we are going to follow these 5 days. It will not be just lecture by me. There are another faculty members of the Mechanical Engineering Department which are also participating. By the way, I thank you very much the kind invitation from Dr. Banerjee and also from Dr. Vivek Kalyankar to give this lecture that was scheduled for before the pandemic, but besides that, we were able to keep the contact, and finally, after the pandemic has relatively finished, we have been able to prepare this course. I am very happy and honored to be here in Surat and in India. So the aim of this course, just trying to explain a little bit about the title, is to provide fundamental understanding about microstructure controlling mechanisms in metals. We will be giving special emphasis on grain refinement as the main method we have to control the microstructure in metallurgy. We will be focused basically on thermomechanical processing. We will be talking about severe plastic deformation and also and especially about welding. This will be another of the topics involved in this course that will be lectured by Professor Vivek Kalyankar and colleagues. This is an overview of the lectures that we are going to have, but don't follow that. Follow the one that Kalyankar has shared with you, has distributed with you, because we have done some minor modifications in the sequence, not in the titles of the talks, but in the sequence of the talks. First, I would like to do some small introduction about where I am coming from. Although I was born in Canary Island, I live in Barcelona. Barcelona is a city which is in the northeast area of Spain, close to the Mediterranean Sea. So you see here, this is the sea. The weather is, let's say, Mediterranean one. So heavy summers with a lot of humidity and moderate winters. The city is well known by their distribution, how it has been planned, the expansion of the city, and also is known because a lot of architectural buildings, significant architectural buildings, like the Music Palace, the Olympic Pavilion, the port. Barcelona has an important port, one of the most important in the Mediterranean area. This is the new skyline of the city, at the north of the city. The famous walkside of Las Ramblas, where all tourists go there. This is Colón signing to the wrong direction because he's signing to the sea, and America is in the opposite direction. Also, it's very well known because one of the most famous architectures, Antonio Gaudí. Gaudí is the architecture of these two famous buildings, and also and especially this one, the Temple of the Holy Family, which is almost being under construction since the last 150 years, but it's expected to be finished in just 10 years more. So now we can enter into the building. This is an image of the interior of the building, which is really impressive and very nice. However, most probably Barcelona is better known because these people, right? And this is a problem for me because I am supporter of Real Madrid. So I live in the wrong place. So maybe you are questioning why I'm putting this here, and the reason is because here you can see the engineering faculty. Yeah? The old engineering faculty. It's very close to the stadium of Barcelona. By the way, none of them are playing already here in Barcelona's team. They are retired or they are in different teams. This is the old engineering faculty, which is the oldest engineering faculty actively running in Spain since 1851. Although, to be honest, the oldest one is the one who is in Mexico, when Mexico was part of the Spanish Empire. So the first engineering faculty in Spain was not created in mainland, but in Mexico. Not many people know that. Yeah. You know, we are in Europe, and in Europe there is a large tradition of very famous and renowned professors. Especially Italian people, they are saying, Galileo Galilei was Italian, Leonardo da Vinci. Well, unfortunately, we don't have these people here, but once Albert Einstein visited our faculty a long time ago. Anyway, now we are in a new campus. We are just across the city. The old campus was here, and now we are very close to the beach, which is a very good initiative to attract foreign students. Probably this is the campus closer to the beach in Europe, I would say. Just 5 minutes walking or 10 minutes walking, depending on the beach you want. So in this new campus, we have also new facilities, new brand facilities, because taking chance of this moving, we have renewed our laboratories. And these are some images of the laboratories and the facilities. This is finally the location. I was saying that we are located in 7 different campuses, but the distance between them is not too large, at least in comparison with India's distance. Here we have only 40 kilometers from the farthest place to the other one, but different cities, finally. These are some figures of our university. We are a public university, carrying out research and higher education in the field of architecture, engineering, science, and technology. We are around 30,000 students, 3,500 teaching and research staff. Probably the most important figures are here. We are the #1 university in catching sources for R+D, especially connected with industry. We are the university that get much more direct money from industry for doing research than the others in Spain. The total budget is 350 million euros, and 70 million come from R+D. This is a video of our university. Just it's a small video to have some fun with some modern music, to have an idea about what we do in our university. We tested before, but you know, Microsoft is always okay. Change the world. All the campuses appears in this movie. now it's your turn. Come to UPC. So I have to say that the university at undergraduate level is basically formed by local people, for Barcelonan people and Catalan people, but at the master and PhD level is absolutely international. We have especially people from Latin America, but not only from that. We receive people from Central Europe, France. I have even had some Indian students at master levels, even in my research group. So we receive from abroad, and it's the typical language we use when we work all together is English, right? In our department, the Material Science Engineering department, we have two sections. One section is devoted to textiles engineering, which is also heavy field in Catalonia, like here in Surat. So textile engineering is very, very important. And the other group is devoted to the classical material science, divided in 4 different research groups. One oriented to biomaterials, biomechanics, and tissue generation. Other one to structural integrity, micromechanisms, and reliability of materials. Another on polymers and composite technology, and the one I lead is the one devoted to metal forming technology. PROCOMAME in Spanish, Procesos de Conformado Materiales Metálicos. Since 1 year ago, the rector of my university appointed me to be the general director of the foundation CIM. CIM comes from Computer Integrated Manufacturing. It's a research center that has 30 years old, and is nowadays is mainly devoted to additive manufacturing. We work also on advanced machining and metrology and rapid prototyping, but the main core right now is additive manufacturing. Indeed, in the past, we create our own technology for fused filament modeling or deposition, and this creates a company, a spin-off, Barcelona 3D, which now works in that area, in filament deposition, but now we are working in our own technologies in different fields. For instance, and this is another video, we now manufacture direct ink writing printers. In these materials, we don't work with filament, but we work with pastes, or inks. We mix a polymer with metal or with a ceramic, and then we make a mixture, and then with a shearing we press, and then we distribute all the material, doing layer by layer, printing the different components. This is technology developed by us, and we sell these types of printers worldwide. We can work with different materials, multi-materials. We can work under controlled atmosphere to avoid oxidation or reactions with the environment. We can keep constant temperature while printing. We avoid contaminations also. And this is technology developed in our CIM center. A way to do tubes by 3D printing. So this bar is giving a round, while the header is just extruding the material. And then the other technology I would like to show you is a technology we are developing for printing cements and concrete. So we can go to the next, that one. So in this case, the printer is quite large, because we want to print buildings, or similar. So So here it's very important to control the viscosity of the cement. Otherwise, you cannot do layer by layer. You cannot construct layer by layer your material because it will be spreading. So the viscosity is the key point here. On the header you have in your printer to control that. The basics is relatively simple. It's just to be able to control in X, Y, Z a header. If you know that, then you only have to know what you are feeding in the header at the scale that you want. But basically, it's more a mechanic work than a metallurgical work or materials work, but also is connected. And nowadays we are developing 3D printing systems for metallic components. Particularly, we are working with wire arc additive manufacturing, which is indeed robotization of TIG or MIG welding systems. Right? Okay, with this I finish the presentation and then we go with the important thing today, which is the lecture number 1, which is related to understand the mechanical properties, the importance of the microstructural control in materials. Lecture number 1. So we are having just an overview of microstructural control in structural applications. Well, I assume that most of you are or have some connection or some basics of material science to understand about what important is the microstructural control or the microstructure you have in a certain application. Remember that we are referring for microstructural control the manipulation of the microstructure in order to achieve specific properties and performance characteristics. And we are talking especially now on mechanical properties. We can do the same with electrical properties or magnetic properties or thermal properties, but in this case, in this course, we are basically talking about mechanical properties. And the way to control the microstructure is very diverse, but the most important one is, for a given chemical composition, is through the processing method that we are going to use. The processing method that we select will be indicating what is the microstructure that we are going to obtain, and therefore the mechanical properties that we are going also to get. Is a key factor for us to be sure about the microstructure. If you are a mechanical engineer, most probably you are much more worried about the shape of your components, the tolerance, the dimensions. But if you are a metallurgical engineer, you are much more concerned about what is happening in the interior of the material, what the microstructure of the material is. So for us, indeed, a component are mechanical properties with shape. Okay? While a mechanical engineer doesn't care too much about mechanical properties, but much more on the geometry and the shapes and the tolerance. Of course, we have to work together. I'm not saying that mechanical engineers are wrong or metallurgical engineers are right. Indeed, when I tried to be mechanical engineer, I failed, absolutely. I tried once to design a die, and then it was a complete error, a chaos, because I never asked a mechanical engineer how to do that. Because I didn't know. I was metallurgical engineer, so I am much more involved in the microstructure, in the internal behavior of the material. And this is very important because this microstructure is conditioning the mechanical properties that you get, the in-service properties that you get, which is finally what is important, together with the geometry, of course. So for us, material science people, we usually work with this famous tetrahedron. In this tetrahedron, we have in one vertex the microstructure, in one corner is the microstructure, in the other corner the properties, the mechanical properties, other corner is the performance, and then we have the processing corner. And in the middle, we use characterization techniques to understand the microstructure, the properties, the performance, or whatever. Okay? The important thing here is that every corner is connected with the other point. So you cannot analyze what's happening with your material just checking the processing, or you cannot analyze what's happening with your material just checking the mechanical properties or just checking the microstructure. Everything is connected. In the last, let's say, material science is a relatively new field of engineering, which at the very beginning was much more oriented to identify microstructures and mechanical properties and connecting both of these, microstructure and properties. So most of the research was done on understanding this connection, this edge. But sometimes forgetting the performance, usually until just a couple of decades, forgetting about processing. But this has changed dramatically in the last 20 years. Because now we know that new processes are promoting also new materials, even keeping the same chemical composition. So that's very funny. While having the same chemical composition, and we will focus immediately in steels, we can get a relatively different material with new mechanical properties, unexpected indeed. Remember also that materials has been ruling the history. They are indicating who is governing, which empires wins over others, just by having control of the most important material at those days. This is a typical Ashby plot, Professor Ashby from Cambridge, in which he graphed the relative importance of a material. Don't tell me how you measure relative importance, something quite subjective, against time, and time is not in a linear scale and it's not in a log scale, it's an arbitrary scale. You see, because here is 10,000 before Christ, then here is year 0, 1,000, you see, here is only 10 years, somehow reminds to a log scale, but anyway. And what you see is how materials were important since the very beginning. So metals were not important because the humanity only knew gold. Polymers, natural polymers were very important, wood, skins, fibers, composites for doing bricks, ceramics, only stones. Yeah? But then with the development of humanity, metals start to be much more important. This is also the age of copper, the age of bronze, the age of iron. And here we have the moment in which the Industrial Revolution started in UK and in Central Europe, with the developing of a new fast way of producing steel. Okay? So that's why the steels in that moment starts to be the most dominant material. Well, this was accompanied because there was almost knowledge about polymers, nothing about composites. The most important fact in ceramic was cements and glasses. Well, there is a moment in which there is the development of polymers, and then new metallic alloys appears, like aluminum, new high temperature alloys, superalloys, new materials like titanium, zirconium appears. Although new ceramics start to appear, new technical ceramics, the most important material in the 60s and the 70s were metals. But since that moment, things are starting to change again, because we are starting to find a lot of applications for polymers. New composite materials, polymer-based, are available now for us. And then new technical ceramics also appear into the market. Indeed, the graph was relatively predicting the future when I start to teach, but now the graph is past, is history. So it's 3 years old at least. But you see what's happening. Again, new metals, the metals are reducing the importance, but this is not really true. What is here happening is that new alloys are appearing into the market, especially regarding to steels, which makes steels still the most important structural material. I think we can skip this. Of course, this is the classical classification of materials. I can skip that and go directly to the classification of metals, which is basically iron-based alloys, non-iron-based alloys, and all of these stuff that which are not iron-based alloys too, but they have specific properties. Refractory metals, they are able to wear at very high temperature, 1000, even higher temperature, but they cannot be in touch with oxygen because they almost sublimate. They pass from solid to gas state in contact with oxygen. So, well, you can use it, but then you have to control the atmosphere. Superalloys, nickel and cobalt-based alloys, which are materials resistant at high temperatures, but at intermediate level, let's say 600, 700 Celsius. Metallic glasses, which are not crystalline materials, they are amorphous materials. And a new family, the so-called intermetallics, in which you make components with two metals in a sort of molecule with a well-established stoichiometry. Well, I told that I will not enter into too much detail about that. I assume that most of you know what is a steel. Basically, it's an iron carbon alloy with relatively low amount of carbon. And when this material was discovered, since that moment is the key factor of the Industrial Revolution. Structural materials appears in the 2 centuries ago. And nowadays, you check, I like very much to show this slide to my students to convince them that they are not wrong if they have studied steels. You know, in material science department, people say that the steel is an old-fashioned material. Everybody knows about the steel. There is nothing to do new in steels. And then people just is starting other kind of materials, titanium, aluminum, magnesium. Sorry for the magnesium guy here. But look at this table. Look at this graph. This is the world production of metals in 2008, and here is actualized to 2021, some data. This is the steel production. Sorry, this is in Spanish, acero. Steel is today is around almost to 2 million tons. The rest of metals, all together, if you add all the rest of metals, aluminum, copper, zinc, lead, magnesium, titanium, the addition of the rest of metal is almost 1 order of magnitude below the steel production. So that means that even if tomorrow a new material appears, it will be almost impossible to replace the installed production facilities we have in the world. So there is still a long life for steel. So steel, furthermore, is reacting, promoting new materials, new alloys, better. And you see, aluminum is only 50 million tons nowadays. Nothing in comparison with steel. Copper is used just for basically for electrical application, because it's the cheaper commercial alloy for electrical conductivity. You know why zinc is the 4 in this scale, in this graph? Because steel has a problem with corrosion, and we use zinc with a thin layer of zinc of just a few micrometers to protect iron from corrosion. So this thin layer of a few micrometers on iron makes that thin is the fourth metal in the world, and because you have to protect this almost 2 million tons of steel. Then lead, which is now almost forbidden because contamination problems, magnesium, titanium, okay? I'm not saying that aluminum is not important, magnesium is not important, titanium is not important. Of course they are important. Indeed, if you work in aluminum, copper, zinc, lead, magnesium, and titanium industries, the added value is higher than the one we have in steel. That's the point. Except if you manufacture special steels, in which the added value increases a little bit. But if you are working with carbon steels, the added value is so low that depends on the price of the scrap. So most of the time you cannot control very much. But if you think in global terms, any slight improvement that you promote in steels will have a big impact in humanity, that a slight improvement in titanium. If you are able to reduce the footprint, the carbon footprint of steels just 0.1%, you get much more impact in humanity than reducing 10% of the impact of titanium manufacturing. Okay, so if you have decided to study steel, there is a lot of work. There is a lot of work to do, and a lot of interesting work to do. So we are going to focus on that, and remember that we were talking about microstructure, and the way to control the microstructure, especially if we are talking about these metals, is by controlling the processing method that we have. In a summarized word table, we can say that these are the most important processing methods: casting and solidification. I will not enter now into detail. Plastic forming, this will be the topic we will start this afternoon. Machining, welding also as a way to join metals, which is when are difficult to be manufactured by casting or by plastic forming. Powder metallurgy, in this case your raw material must be in the form of powder, and this will be controlling the mechanical properties. Remember that when the material is coming from the sintering way, usually the mechanical properties are relatively low because the material has porosity. Also the chemical composition is not very homogeneous. So there are some drawbacks with these processing methods. So it's important for us to be able to predict the microstructure, because if we predict the microstructure, we are able to predict the mechanical properties in a given shape. So both mechanical engineers and metallurgical engineers should work together with this main purpose in mind. But nowadays, we are starting to have a lot of new different processing methods that sometimes doesn't fit to the old classification. We have semi-solid forming. Now there are some people that heat the metal up to a temperature in which you achieve a balance between solid and liquid phase. So if you get 50% of solid phase and 50% of liquid phase, what you get is something like the sand in the beach. You know that you can easily deform, although if you try to deform, the load units are very low because they cannot resist shearing because the liquid phase. But you have to keep a very careful control of the temperature to be sure that you are having 50% of solid and 50% of liquid. For those of you who are familiar with the phase diagrams, you know that there is a point at a given composition, there is one temperature at which you can achieve this balance, 50% of solid, 50% of liquid. Another process available today is the so-called metal injection molding. You mix metallic powder with polymer, and then you inject this mix into a mold. When the process finishes, at the binding system, you evaporate the polymer, and then you get a metal, which is basically powder, that you have to sinter. So here you are mixing the good things of sintering with the good things of injection molding in polymers, okay, or injection metal casting. Yeah. Another process is hydroforming. Use oil or water to introduce a component within a die and use the pressure of this oil or water to distribute the stresses in a more homogeneous way than in a forging process or in a sheet forming process. Yeah. Hot stamping. Usually when you want to deform a sheet, a flat format, usually you think in doing that at cold conditions, at room temperature conditions. No, now most of our cars are coming with components which are hot form. And during the hot forming process, we are going to change the microstructure in such a way that we will get a very strong and hard material. We will see in a moment. Incremental forming processes. Instead of deforming all the piece in one single stroke, we can do a small increments in the piece by just a sort of punch, and then distribute this deformation along the piece in an incremental way. And we will observe that we can deform much more than if we want to deform the entire piece in one single hit. Severe plastic deformation methods. This is one of the topics we are going to talk in the next days. With this technique, we are going to break paradigm. You know, how much you think you can deform a metal? When you do a tensile test, how much is what you can deform in percentage, more or less, just having a value? 1%, 10%, 1,000%? Any idea? Who works in a metal laboratory? How many of you have done a tensile test? What is the typical elongation that you get?
For sheet metal, 20 maximum.
In terms of elongation, in percentage?
Yeah,
20, 30%, something like that, plus minus that value. Okay, I will going to show you a method in which we can deform at room temperature, at cold conditions, 1,000%, 2,000% without breaking the material and refining the microstructure at the same time. Okay, and obtaining an ultra fine grain material or a nanostructured material. Okay, so new applications appears when you are introducing new deformation processes. And then today, the famous word, the famous system, additive manufacturing, which appears in contraposition to the subtractive manufacturing or the the machining way of manufacturing the materials. All of them are giving different microstructure, and therefore new mechanical properties appear. And we can say that if we are promoting new mechanical properties, we are having a new material. Okay? At least I will accept that as a good answer in an exam. Okay? Well, how we can control the microstructure? We can control by controlling the grain size, for instance, which is the key microstructure feature for materials engineer. So we can get dendritic microstructures, equiaxed microstructures, elongated microstructure, depending how we are manufacturing the material. And depending on that, we will get different mechanical properties, even keeping the same chemical composition. We can do some microstructural control by promoting phase transformations. Heating to a given temperature and then controlling the cooling rate. And then we can get thermal treatments, recrystallization, and all of these are very well used in welding or in heat treatment processes. We can control the metallographic texture. Metallographic texture refers to how the grains are oriented into the space. You can have the same chemical composition, you can have the same microstructure, you can have ferrite in the steels or perlite in the steel, but depending of this ferrite or perlite is preferentially oriented into the space, you are promoting different mechanical properties. This is what we call texture, metallographical texture. And this is important, and this is controlled by the process, especially rolling processes or annealing processes are controlling the texture that you get. This is important for instance, in electrical steels to enhance the magnetic performance the electrical steels can provide. Or even for carbon steels, the one we use in the automotive sector, because depending on the texture, you can get more formability in your material. Okay, so this is important. So remember that you as a mechanical engineers, you have some hypothesis at the very beginning, right? You say your material is homogeneous and isotropic. So this is because it's very easy to design when the material is homogeneous and isotropic. But if you are able to control heterogeneous materials and non-isotropic materials, then you can get a lot of new properties in the material. But you need to know how to control that. That's the point. So it's not necessarily bad news that your material has texture or is anisotropic or is heterogeneous. The problem is how to design with that. So easy design, simple design, homogeneous and isotropic. So if your material is heterogeneous and anisotropic, then you need more knowledge to be able to design that material.